Welcome to Unit 4. In Unit 4, we're going to go over Chapter 3.1 and 3.4. We're going to learn more about derivatives and different rules involved in derivatives. Specifically, we're going to learn about the chain rule and derivative of logs in this unit. So before we start talking about what the chain rule is, let's talk about why it's important. So here, for this first problem, how would you differentiate f of x equals 3x plus 2 squared? Well, as of right now, you have two different ways you could do it. You could FOIL it, so we have 9x squared plus 12x plus 4. And then I take the derivative of that using the power rule, 18x plus 12. Or the other way that I could do it is using the product rule, which would be to create my u and my v. So my u is 3x plus 2, and my v is also 3x plus 2. And then my u prime is 3, and my v prime is also 3. And then I use the product rule for f prime of x is 3 times 3x plus 2 plus 3 times 3x plus 2. And then let's see, we get 9x plus 6 plus 9x plus 6, so 18x plus 12. So for this problem, we actually have two different ways to solve it, and both of them were equivalent at 18x plus 12. However, how we solve this problem? That would be a lot of FOILing 3x plus 2 to the 100. That would make it very difficult to FOIL out. It would also make it very difficult to use the product rule. Writing something out 100 times would be really cumbersome and a waste of time. So that's why we're going to use the chain rule. The chain rule is much more geared toward these higher powers, and they let us solve these with a lot of ease. So this is going to be another rule that I'm going to read to you what the book's definition is, and then we're just going to talk about what it means. So if a function g is differentiable at x naught, and a function f is differentiable at g of x naught, then the composite function f of g is differentiable at x naught, and f of g prime equals f prime of g of x times g prime of f of x. You could also have written it using the different form of dy over dx is dy over du times du over dx. So let's talk about what this actually means. We're going to differentiate the parent function. So if I have f of g of x, I can write that out as f of g of x. So I differentiate the parent, f prime of g of x, and then I differentiate the baby, the thing in the middle, times g prime of x. This is probably the easiest way for you to see it and for you to keep it in your notebook. This is super important, and we will use this all the time. Now let's apply it. When I look at this in example 1 on page 222, it asks me to find the derivative of y equals x cubed minus 4x plus 1 to the 100. So the first question is, what's the outside function? What's the function that's the parent function? So hopefully you see that the the power to the 100 is the parent function. So if I was going to have my f of x would be x to the 100, and my g of x would be x cubed minus 4x plus 1. So my parent, my f of g of x, is the whole function together. X cubed minus 4x plus 1 all to the 100. So first let's differentiate the parent. So if I look up here, my f prime of x would be 100 times x to the 99. And the baby, the inside function, their derivative, would be 3x squared minus 4. That would be g prime of x. Now let's put those things together. I'm going to differentiate the parent, which is this to the 100. So my y prime is going to be 100. The baby stays alone. X cubed minus 4x plus 1 to the 99. So that's the power rule. The same power rule that we saw up here when it was just x to the 100. 100 times x to the 99. So the 100 came down, and I take 1 minus it, and I get to my 99. Now I have to differentiate the baby. And here's my baby. X cubed minus 4x plus 1. So I multiply by the derivative, which is 3x squared minus 4. And I don't have to do anything else to it. I can if I want to, but I certainly don't have to. I can leave it right there. It looks like we've run out of some room for part B, so let's put that on the next slide. Y equals cosine of 3x minus pi over 4. So take a second here, please, and see what do you think the parent function is? Who is the outside function? Who is the function that is on the outside that encompasses the baby? Hopefully you agree it's cosine. Cosine is my parent here. So I'm going to take the derivative of cosine, which is negative sine. I leave the baby alone, 3x minus pi over 4, and then I multiply by the derivative of the baby. 3x minus pi over 4, my derivative is 3. Remember, pi over 4 is a constant, so I don't have to do anything to it. So let's just rewrite this so it's a little bit neater. Negative 3 sine 3x minus pi over 4. Of course, you could leave it this way without rewriting, but sometimes that 3 gets lost when you're looking at your notes, so it's a little bit nicer to write it this way. Now don't be afraid of the chain rule seeming a little overwhelming. I promise the more you do it, the more it's going to make sense and the easier it will get. This is definitely something that's a high-level derivative problem. So you're doing a great job already just by following along. Alright, let's take a look at example 2 on page 221. Here we have the function y equals e to the x squared minus 4. So the first question is, what's the parent? Hopefully you think the e to the x squared minus 4, the e part, is the parent. So I'm going to first take the derivative of the e. And hopefully you remember that that's just itself, e to the x squared minus 4. Now I times it by the baby. That's the x squared minus 4, which is 2x for my derivative. So overall my derivative becomes 2x e to the x squared minus 4. Let's take a look at y equals sine of 4 e to the x. So our parent function is going to be our sine. So y prime is cosine, the baby stays alone, 4 e to the x times the derivative of 4 e to the x is my baby, 4 e to the x. Remember, e to the x is crazy like that, and it's the only one that you get the derivative is itself. So my y prime is 4 e to the x cosine 4 e to the x. I'd really encourage you to watch these previous slides a couple times because figuring out who the mom and the baby is can be difficult, and then differentiating them can also be difficult. So take a couple times to go through that before you decide that you have it or you're lost. Alright, on example 3 we take it one step further. It wants us to find the equation of the line. Oops, I think it's supposed to be tangent. Equation of the tangent line to the graph y equals 5 e to the 4x at the point 0, 5. So first thing we have to do is find our slope of the line. We have our x and our y, but we need our slope. So let's first find that, which is our derivative, of course. So y prime, the 5 is going to come for the ride. E to the 4x is our parent, and then we differentiate 4x is our baby, so 4. So 20 e to the 4x. And now I need to find at point 0, or at x equals 0. So that will be 20 e to the 4 times 0, or 20 e to the 0. Anything to the 0 is 1, so my slope is 20. So now that I know my slope is 20, my x is 0, and my y is 5, I can write my equation of my tangent line. Y minus 5 equals 20 times x minus 0. Of course, I can rewrite that if I want, but I do not have to, and I definitely wouldn't. But I'll do it out for this if you want me to. And then we get y equals 20x plus 5. and that's in y equals mx plus b. Again, I always leave it in this form because it takes much less work. But it's your call, whatever you want. Example 5 on page 223 is kind of like a puzzle. It's asking us to first break down this h equals f of g, and then to find h prime of 1. So before we can find h prime of 1, we need to find h prime. So h prime of x is going to be f prime of g of x times g prime of x. So I just used the chain rule. I differentiated the parent, who's my f, and then I differentiated the baby, who's my g. Now let's plug in the 1. H prime of 1 is f prime of g of 1 times g prime of 1. So g of 1 they gave me here is 2, f prime of 2, and g prime of 1 they gave me here is negative 3. Now I need to find f prime of 2. They gave that to me right here at negative 4. So negative 4 times negative 3, the derivative of this composite function is positive 12. In 3.1, we also learn about the derivative of y equals a to the x. So here we have our x is actually our exponent. This is pretty complicated how they got here, so we're going to actually walk through this step by step. But I do want to just show you that the derivative of y equals a to the x is actually a to the x natural log of a. You can certainly memorize this and keep it in your notebook and put it in the front cover, and that's awesome. But in case you forget it, I want you to be able to rederive it if you need to. This is one of those things, unlike the power rule and the chain rule and the product rule, I don't have this one memorized. This one I always have to rederive each time. And there's 2 different ways to derive it. We're going to learn one way today, and then maybe in a couple of more units we'll learn a second way. I honestly use the second way much more often, but that's beside the point. So let's try and derive this one. So the first thing I need to do is rewrite it kind of fancy. I could rewrite this as e to the ln of a to the x. Because e and ln are inverses of each other, e and ln undo each other. So when I write e to the ln, that's the same thing as 1. So it's 1 times a to the x. Now, hopefully you remember from your exponent rules that if I have the natural log of a to the x actually comes out in front. So I can rewrite this as e to the x ln of a. So that's pulling out some old school pre-calculus right there. But I know that you did that, it just doesn't mean that you remember it. Now let's take the derivative. So d dx of a to the x, that means the derivative, equals the derivative e to the x ln of a. Alright, so we're going to use the chain rule here. So this side's going to be y prime, no problem there. I'm going to use the chain rule. E to the x ln of a, well that's the mom, so nothing happens there. That's my parent function. And then my baby is the derivative here. X times the ln of a. Well, x, the derivative of x is 1, and ln of a is just a constant. So 1 times the ln of a. The ln of a just follows along, and I multiply it by the derivative of x. So that becomes ln of a. Alright, now let's do some more reducing. My x is going to go back up to the a, which is the same rule that I did to undo it in this beginning part. So I have e to the ln of a to the x times ln a. And again, e and ln will cancel, so I can ignore those two. And I get a to the x times ln of a. So there's my derivative. Again, this is something that you're going to want to write down in your notebook. You're going to be using this. It's not one that we use very often, but it's one that's super important when we need to use it. Again, you either have to memorize it or be able to derive it each time, because it's not one that's so intuitive like the power rule or the product rule. Alright, so I'm just going to rewrite the rule up here. We have y to the x, and then y prime is going to be a to the x times ln a. So here in this case the a is 2, so f prime of x is going to be 2 to the x times ln of 2. So in part B, we have a little bit more going on. I can rewrite this, because it's a negative exponent, as 1 over 3 to the x. And then I can also rewrite that as 1/3 to the x. Those are all from my exponent rules. It doesn't matter where I put it because of the 1. 1 to the x is still 1. So now my a is 1/3, and it looks exactly like this parent function here, this exponential function here. So now let's take the derivative. So my f prime of x equals 1/3 to the x times the ln of 1/3. All right, so we can clean this up a little bit. We can make this 3 to the negative x. And let's talk about our ln rules. I can make that ln of 1 minus ln of 3. And hopefully remember that the natural log of 1 is 0. It's actually the only one that you have to memorize. So the natural log of 1 is 0. And then I can rewrite this as 3 to the negative x times negative ln of 3, or negative 3 to the negative x times ln of 3. So although this was correct, and if it was an open response, I could leave it just like that, this is what would be on a multiple choice question. So you definitely want to be sure that you're versatile, that you can go back and forth, and that you know some rules. This is the only ln that you're ever going to have to memorize, that the ln of 1 is 0. So try and commit that to memory. All right, for C, it was g of x equals 1/2 to the x squared plus 1. So I'm going to use the same rule again. So 1/2 to the x squared plus 1 times the ln of 1/2. All of that's fine, but I also need to take care of the derivative of the baby. I have to do my chain rule. So the derivative of x squared plus 1 is 2x. So let's do a little simplification here. I have 1/2 x squared plus 1, and then again it will be the ln of 1 minus the ln of 2, and then times 2 to the x, 2x, and ln of 1 is 0, so that becomes 0. And now I have 1/2 x squared plus 1 minus ln of 2 times 2x. It looks like in example 7, they want us to combine the power rule and the chain rule. And here they're making our exponent negative, but it's okay. We know how to handle negative numbers. Nothing crazy about that. Our parent function is to the exponent of the negative 5. So the negative 5 comes down and the baby stays the same. Nothing happens inside here. And then negative 5 minus 1 is negative 6. Now I multiply by the derivative of the baby. 3 minus x cubed is negative 3x squared. And then I can just simplify that. Negative 15x squared all over 3 minus x cubed to the 6th. Let's look at part B. It's asking us to find the derivative of x cubed theta. Now, the most important part about this one is to remember, or maybe to learn if you don't already know, that x cubed is not real. That's not, cosine cubed is not real. That's not how we're supposed to do cosine cubed. We're actually supposed to write it as f theta parentheses cosine of theta cubed. Now this looks like something we can definitely handle. This is shorthand. Cosine cubed is just shorthand, and it's not really useful for either putting it in a calculator or for finding the derivative. It is useful for just writing it quickly. So people have abbreviated it, but it's just an abbreviation, so definitely always rewrite it so that the whole function is cubed. So now let's take the derivative. F prime of theta, the 3 comes down, so 3 cosine theta squared times, and then I multiply by the derivative of cosine theta, which is negative sine theta. And let's rewrite that so it looks a little bit prettier. That could be negative 3 cosine squared theta sine theta. So now we're getting ready in example 8 on page 225 to put the chain rule in conjunction with the product rule and the quotient rule. This has a lot of steps, but as long as you keep things very organized, you're going to be just fine. So let's get started. First, let's see, we have a u and a v, so let's write that out. U is e to the x, and v is x squared plus 1 cubed. U prime, that's nice and easy, it's e to the x. And let's go over v prime. This is where our chain rule takes in place. So the 3 comes out, and we get x squared plus 1 squared times the derivative of the baby is 2x. So I'm going to simplify that to say 6x times x squared plus 1 squared. Now I'm going to do the product rule, and I multiply those two together. So e to the x times x squared plus 1 cubed plus e to the x times 6x x squared plus 1 squared. There's lots of other ways you could write that. You could factor your e to the x out, and you can factor x squared plus 1 squared out of each, but I don't really think that's necessary. Just in case you see something like that, it will help you to be able to simplify it two different ways. All right, now let's take a look at part B. This is a quotient rule. We have two different ways we can do this. We can do the quotient rule first, and then the chain rule first, then the quotient rule. There's really no better way to do it over the other. It's however you see it to be more simple. So I'm going to rewrite it on the next page because I'm going to need some more room. Okay, so let's do it one way first. I'm going to distribute the squared to each piece. So that would be 3x plus 2 squared over 4x squared minus 5 squared. Now let's break it up into our quotient rule. So my u is 3x plus 2 squared, and my v is 4x squared minus 5 squared. Now my u prime is going to be the chain rule. The 2 comes down, 2 times 3x plus 2, and then a derivative of the baby is times 3. And my v prime, the 2 comes down, 4x squared minus 5, and the derivative of the baby is 8x. So I'm going to simplify both of my primes. So 6 times 3x plus 2, and then 16x times 4x squared minus 5. All right, so then I multiply this times this. So 6 times 3x plus 2 times 4x squared minus 5 squared minus the other two. 16x times 4x squared minus 5 times 3x plus 2 squared, all over the original denominator squared. So 4x squared minus 5, and it is squared, so squared squared is fourth. Now I can simplify this. It looks like I have a 4x squared minus 5 in every single piece, so I can reduce that. So let's see. I'm going to cancel off this one, and that means 1 will be left there, and 3 will be left there. So let's rewrite that. 6 times 3x plus 2 minus 16x times 3x plus 2 squared, all over 4x squared minus 5 cubed. And I can leave it just like that. Again, if it is a multiple choice question, you might have to FOIL it differently. You might see an answer differently. They might not have even reduced at all. So you just have to be really flexible when it comes to the algebra and the multiple choice part. Now let's do it the other way. I could have done the chain rule first. So I could have said g prime of x is going to be 2 times 3x plus 2 over 4x squared minus 5 to the first power, and then I have to multiply by the derivative of the baby. So I need to take the derivative of this baby on the inside, which is going to be my u and my v. So my u is 3x plus 2, and my v is 4x squared minus 5. U prime is 3, and my v prime is 8x. So we have this times 3 3 times 4x squared minus 5 minus 8x times 3x plus 2 all over 4x squared minus 5 squared. So I think you'll be able to see that if I multiply some of this out, I'm going to have the same thing. So 2 times 3 and then times 8x, that's where I'm going to get my 6 from. And then 3x plus 2 times 4x squared, that's going to be 3x plus 2 times 4x squared minus 5. And then 2 times 8x was the 16x. And we have 3x plus 2 times 3x plus 2, or 3x plus 2 squared. And then when I multiply my denominator, the 4x squared plus minus 5 and 4x squared minus 5 squared, I get 4x squared minus 5 cubed. So I think that you see we get the same answer. Hopefully you see that. We get the same answer in both of them. It doesn't matter which way we did first. And it's really a matter of preference, because I think that you're going to be able to see that neither one was exceptionally quick. It's really up to you about which one you prefer to do. If you prefer to distribute and then multiply and do the quotient rule, or if you prefer to do the chain rule and then the quotient rule, it's your call. Now let's take a look at example 9 on page 226. Before I get started, the first thing I always do is I remember that this squared isn't real. I need to rewrite it. Y equals 5 parentheses cosine 3x plus 2. Then that's squared. That helps me remember which order I need to do things in. For my outermost function, it's going to be the squared. That's my parent. So we're going to have two babies in this case. Let me back up for a second. We have two inside functions. The inside function first we see is cosine, and then next it's 3x squared plus 2, where my 2 is my parent function. That just means we're going to have to do the chain rule twice. We just keep multiplying by the babies. Let me show you what I mean. So my derivative, the 2 comes down first, and I get 10, and everything stays the same. Cosine of 3x plus 2. Now I multiply by the derivative of cosine, so minus sine 3x plus 2. Then I finally multiply by the derivative of the baby, this last baby here, of 3x plus 2. See how it stayed the same? Now I multiply that by 3, and then I can write all this out as negative 30 cosine 3x plus 2 sine 3x plus 2. I encourage you to try that one again on your own and see if you can get the correct answer. It's a pretty complicated double chain, but if you take it step by step, hopefully it will make sense. Again, for part B, the very first thing I do is I move the cubed to the outside. Oops. So now, again, I'm going to have two babies here. I have my sine baby, and then I have my pi over 2x baby. So we'll just take it step by step, and the first thing I'm going to do is move the cubed out. So 3 comes down, and then I have sine pi over 2x squared. Nothing happens to the babies on the inside yet. When I handle the outermost function, everything inside stays the same. Now let's handle the sine next. So times, the derivative of sine is cosine pi over 2x. And again, nothing has happened to the innermost baby here of pi over 2. That's my next thing that I multiply by. Pi over 2x, the derivative is pi over 2. So now let's put that all together. My derivative is going to be 3 pi over 2 sine squared pi over 2x cosine pi over 2x. Again, I definitely encourage you to retry this one on your own, and hopefully, as you can see, that if we take it step by step, the problem becomes a lot more readily available to solve.